This
Good
is
evening, sir.
Govindnath, sir. Lavanya, can you make sir as host? He is in the name of Siva Kalaiselvam.
I'm doing it, sir. I'm doing it.
Okay, okay, fine.
Slide visible, sir?
Yes, sir.
Okay, fine.
Doctor, shall we start, doctor? Doctor?
Yes, sir, we'll start, sir.
We'll start. Okay. Mr. Raja, who is the president of East Chennai chapter, will give a small introduction about our RefCode 2023 event, and you'll also play a video on RefCode 2023, sir. Over to you, Mr. Raja.
Thank you, Krishnamurthy. Good evening, everyone, and thank you for joining in this webinar. I thank the speaker for accepting the invite and be a part of it. Thank you, sir.
Thank you.
To brief you a short, RefCode is a flagship event of history, Indian Society of Heating, Refrigerating and Air Conditioning Engineers. RefCode is the largest exhibition in the country focusing on refrigeration and cold chain industry. It's happening on October 12, 13 and 14. By and large, if you see or search in Google, if you can find many numbers of expo related to food and beverages, probably once in a month, you can find an expo which is happening somewhere in the country related to food and beverages. But this exhibition, refrigeration and cold chain, we tagged as RefCode, is the only expo happening for the refrigeration industry for the benefit of consumers, retailers, traders, and contractors related to the refrigeration industry. Our focused industry are dairy industry, seafood industry, pharma industry, poultry, healthcare, logistics, agriculture, horticulture, and floriculture. RefCode is conducted every year, and this is the 6th edition, which is happening in Chennai. And of course, after 25 years, we Chennai chapter is conducting an expo in this large scale for the benefit of refrigeration industry. The theme of this RefCode this year is Preserve Through Innovation for Better Future. We expect to have nearly 200 exhibitors from the refrigeration industry to participate in this exhibition. A lot of interesting things organized in this expo. Seminars by stalwarts and eminent speakers in the industry, and few international speakers are coming as speakers for few topics. and government of Tamil Nadu and Avin have given keen interest. And today we met the Minister of Milk and Dairy. He gave an assurance that our Avin will participate in this. And last month we met Milma from Kerala, and they also supported us. They gave the confirmation that they will participate to as much as the extent they can. This is the bridge this expo is a bridge between the end user and also the exhibitors. That is the traders and companies who are into the refrigeration industry. They will be showcasing their products, and which will be useful for the industry end users to reduce the energy and to help to begin a sustainable world. In this note, I request you to just note the calendar dates, October 12, 13, and 14. And I would like to just share a short video on this.
Raja, doctor has to unshare, only then you can.
Yeah.
Doctor, you have to unshare your screen, doctor. Only then the video can be played, doctor.
I will.
I think he's already done that.
Yeah, it's
Okay.
done.
One second, sir. Is my screen is visible?
Yeah, yes, sir, it's visible. Fine.
Yeah, visible.
Yeah.
Sir, the audio of the video is not available, sir.
Favorable government policies in the wake of the law. Opportunities. But the issues can handle the genuine grace. It's a signal. But it's I think it's millions. Over 200 exhibitors, intimate to the innovation of the being
Yeah. This is the video, and I request all of you to just register and be a part of it. We will assure you that you will just get definitely some knowledge and key aspects and future innovative projects in the field of refrigeration. Now I request Mr. S. Sriram sir to just say a few words about the hackathon awards related things. Over to you, sir.
I'll keep it very brief as we want to focus on the webinar. With Anna University Incubation Center, we are in the process of conducting a hackathon where more than 120 teams from all over the country applied and 15 teams were shortlisted. We had a boot camp and a pitch between the 4th and 5th of August. 4 teams have been selected to be mentored, and their prototypes will be on display during the Refcold show between October 12th to 14th. We also have a lot of innovative programs in the seminar. My request would be to all of you to visit refcold.in and register yourself to participate, to visit the expo from 12th to 14th October. Thank you. Over to Raja.
Thank you. And thank you, Krishnamurthy, and over to you.
Mr. Venkatesh, who is the Secretary of Chennai East State Chapter, will introduce our speaker. Over to you, Mr. Venkatesh.
Yeah, good evening all. I'm glad to introduce our Professor Mr. Kalaiselvam to you. Very energetic, dynamic, and very interesting person. He basically received BE Mechanical Engineering from Government of College of Engineering Tech, Salem from 1997, and did a Master of Engineering, Refrigeration and Air Conditioning, and a Ph.D. from Anna University. He has been working as a professor, Department of Mechanical Engineering, and the founder director, Center for Industrial Safety from 2013 to 2013 to 2022. He is the head of the department and applied science and technology at Anna University. During his tenure, head of the department, and he successfully inducted a B.Tech program in petroleum engineering and and the M.Tech program in industrial safety and hazardous management. His research interests include nano and micro heat transfer, renewable and sustainable energy storage, phase change materials, nano synthesis, and nano composites. He published 104 technical papers in various international journals, 12 patents, 2 books, 6 book chapters, and 90 more in the national and international conferences. He guided 94 master degree research projects, 2 PDF, 13 PhD research projects so far, and presently supervising 1 PDF and 11 PhD research works, and also master level projects too. He has been in the top 2% scientists across the world, according to the analysis compiled by researchers from Stanford University, USA, in the year of 2020. He received Tamilnadu Young Scientist Award in 2014 by Government of Tamil Nadu, Active Research Award 2013 by Center for Technology Development and Transfer from the former President of India, Honorable Dr. APJ Abdul Kalam, Best National Social Service Program Officer 2010-11, Young Mechanical Engineer 2010 Award by Institute of Engineers India, Young Scientist, and many more. And invite Mr. Professor Kalaiselvam to the program. And over to you, sir.
Okay, so thank you. Thank you for the nice introduction. I'm audible, sir.
Yes, sir.
Yes,
Yes, sir.
I can share.
Yes, sir, you're audible, sir.
Yeah, fine. Thank you. Slide visible, sir.
Yes, sir.
Yes, sir.
Very much.
Okay. Thank you. And again, I'm thanking the organizing team for this webinar. And again, I'm highly privileged to be the part of this ref goal for this particular year. And this evening, the title for this seminar or webinar is Sustainable Thermal Energy Storage using phase change materials for cold storage applications. As far as this thermal energy storage, that is the phase change material used in case of thermal energy storage. It's not only used in cold storage application, it's also used in various heat storage applications. So here in this first slide, the first one is for this particular figure. This is for supercapacitor applications. And we also developed a phase change material for this helmet cooling. We also developed the phase change material for thermal jackets. And similarly, so we also developed a lot of phase change material for cold storage application. Even in case of this short video, they have shown the banana ripening. We have also solution for that. We also developed best storage for the banana ripening and other vegetables such as tomato and other products, how it can be stored effectively without spoiling the content. And I am the professor, Department of Mechanical Engineering. In addition to that, I'm also the director, Center for Industrial Safety, Anna University. So this is my small profile already from history. They have well elaborated my profile. This is my research credentials. And whatever the stuff that we are going to discuss is mostly from the two reference research book. One is the Thermal Storage Technology for Sustainability, System Design and Assessment Applications. This is the academic press publications, that is imprint of Elsevier, USA. The other book is the research edited book, that is again an international edition by Springer, that is nano and biotech based material for energy building efficiency. So these are all the awards and orders already from history. They have well explained this. So now we'll move on to this today's topic, that is phase change material. So here in this particular slide, it shows the activated carbon dispersed heterotic phase change materials for cold storage applications. So this is our.
Excuse me.
Yes, sir.
Sir, we're not able to see that presentation. Just first sheet we are like.
Slide is not moving, sir.
No, it is not moving, sir.
We are stuck in the first page, sir.
I'm the sixth slide actually.
Oh my God. We are still on the first page.
Okay, can I unshare and again open it?
Please, sir. Please, sir.
Okay, sorry. There's a technical glitch. Is it okay, sir? Can you hear me?
Yes, sir, it is okay, sir.
Now on the second slide, is it okay?
Yes, sir. Thank you.
Now I'm in fourth slide. Is it okay?
Yes, sir.
Good. Now we'll move on to this today's topic, that is activated carbon dispersed eutectic phase change material for cold storage. So in this particular case, this is for the banana ripening. So this is a cold storage system where we store our food products or any preservatives. In case of a conventional air conditioning system, we have a chiller unit. The chiller unit supplies the cold energy and it has sent it to the cold storage unit, where it takes the heat and again it returns back to this chiller unit. But in case of the cold storage system with thermal energy storage system, there is an additional circuit. That circuit is nothing but a TESS, thermal energy storage system. This thermal energy storage system will store the excess energy that is available in the chiller unit. And during the part load operations or during the part load hours, the excess cool energy, or sometimes in some other cases it may be a heat energy, the excess heat or cold energy that is stored in this particular storage tank during the peak or peak load hours, the excess energy stored in this storage tank can be used to maintain a proper temperature in a cold storage system. So normally what happens if you use the conventional chiller for storing or to maintain a constant temperature, sometimes there may be a possibility of temperature fluctuations inside a cold storage system. If you have a thermal storage system, in addition to this, that will take care of constant temperature maintenance inside a cold storage. So here, this is the normal load pattern. So maybe in the morning at the time of starting, we have a higher load. Then the load pattern decreases. Then this is the general load pattern of any HVAC systems. So the intention of this particular thermal energy storage system is, so here, this is the load, right? This is the load that reduces. And again, this whatever the load, the less load or the part load can be shifted to this peak load. So normally in case of a conventional HVAC design, we used to design an air conditioning system or cold thermal storage system for a peak load, right? So here we used to design, this is the load at which we used to design a HVAC or a cold storage system. If you include or if you have the test system into that, so instead of designing a cold storage system or HVAC system to this peak load, you can design a system for this particular peak load. Hence, if the load beyond that, this particular load will be taken care by whatever the energy that's stored in a storage tank or test storage tank. This is a pictorial view of the ice storage tank for off-peak load shifting. So for this, the storage of energy, cooled energy, we have this thermal energy storage system. And this thermal energy storage system can be used in case of solar thermal. So as I told that this thermal energy storage is not only can be suitable for cold storage. It's also used for the heat storage. So normally in case of the heat, right, whatever the heat energy that is available during daytime, it's also stored in a storage tank, and it can be used during the night time for drying applications. Similarly, the other application of this particular thermal storage systems are solar thermal power, biomass, heat pump, and district coolings. These are all the various applications of thermal storage systems. So here the main function is supply demand matching, peak savings, and the flexibilities. The main parameters to be considered for selecting this phase change material is quality, capacity, storage density, and what's the power requirements. And again, in case of the thermal storage technologies, we have three types of storage technologies available. One is sustainable heats, latent heats, thermochemical heats. In case of the sustainable heat storage, so this enthalpy versus the temperature graph, the heat capacity of the material will be this. But in case of the latent heat, that is phase change storage or phase change material. So here the example of latent heat storage is water is a very good phase change material, organic and inorganic PCMs. If you plot a graph for enthalpy versus temperature, it will be, the pattern will be like this. This is our storage, the test storage. In case of thermochemical heat storage, so the enthalpy versus temperature graph will be like this. So out of this, the best storage method is latent storage. That maybe in forthcoming slides, we will stress why this is so important. And this is the temperature versus the storage heat. So this is the sensible storage, and this is the sensible storage, and this is the latent heat storage. So mostly, depending upon the requirements, we used to select the phase change material for this, the temperature ranges. If you have a test system in a cold storage system, the temperature fluctuations only within this. Okay, here the characteristics of PCM is high thermal storage capacity, so isothermal storage process, reversibility of process, so volume variations. And again, the only disadvantage of this particular phase change material is it's a low thermal conductivity. For this, to improve the thermal conductivity, there are various methods are available. We are going to discuss that in the forthcoming slides. So here you might have asked why the heat energy can be stored in a sensible, right, instead of latent. So this is storage capacity in case of a sensible storage capacity. The same, that water is a very good phase change material. If the same water can be used for a sensible heat storage, the heat capacity is only in the order of 50 units. In case of a stone, it's less than that. This is a wood for storing the sensible heat. This is plastics, right? If you use the water or any other phase change material for storing the latent heat, the heat storage capacity is increased. Here it's more than 5 times. That is why the people are looking more towards the phase change material for storing the heat. So these are all the various type of phase change material that is available. So here I told that sensible heat storage, latent heat storage, and chemical storage. And our concentration is mostly on this latent heat storage. Even in case of a latent heat storage, we have solid storage, solid liquid storage, liquid and gas storage, solid and gas storage. So under this classification, we have pure materials, mixtures, and heterotic mixtures, right? So in case of the pure and organics, in case of a pure PCMs, we have organic and inorganic PCMs. The organic PCMs are paraffin or plant-based materials or fatty acids. In case of inorganic PCMs, it's water, salt hydrates, and metallics. And again, in case of a mixture, this can be mixed, or even the organic can be mixed, or organic and inorganic can be mixed. In case of HET, so we can mix organic and organic HET PCMs. We can also inorganic and inorganic, and organic and inorganics. So by maybe to have very low temperature requirements, mostly we go for a heterotic phase-change materials. And this is the temperature range that can be obtained by using this phase-change material. If you use alcohols as a phase-change material, the temperature is -100 to -20 degrees centigrade. We can maintain a temperature in a system by using alcohol. If you use an heterotic phase-change material, it go up to -65 to 0 degrees centigrade. And this is for plus temperatures. We have a metallic, high temperatures, hydrated salt, organic substance, and solid phase-change materials. And these are all the PCMs, the type of PCMs that is used in case of an industry. And these are all the fusion temperature. Suppose if you want to store an object at 40 degrees centigrade, you can use this particular combinations. So these are all, you can take a plus 10 degrees centigrade, right? And this is for the higher order higher order temperature, phase-change temperature. As far as our topic is, this is for cold storage applications. Normally, in case of cold storage applications, this may not be suitable. This can be used for storing the heat energy, right? And as far as this particular stuffs are from the reference, this is source for this particular stuff. And this is for mainly used for cold storage applications. We have the melting temperature of -86 degrees centigrade. So this can be best suitable for storing up to -76. Suppose if you want to maintain a -76 degrees centigrade or 75, or in the range of 75 degrees centigrade, you can use this particular combination of heterotic phase-change materials. So we have the phase-change materials at -67, around 50, -33, and these are all the various phase-change material that can be used in case of cold storage applications, very particularly for the cold storage applications. And this is the phase-change material. If you look at, so far I'm talking the content, right? So if you want to visualize the phase-change material, this is the granules, right? The phase-change materials, it shows like that. And this particular phase-change material will be stored in a encapsulator, right? It's a cylindrical encapsulation. And this particular powder or this particular material can be filled into this phase-change material balls. And the ball diameter is in the order of, this is a micro encapsulation. This is a different story. And this is maybe like maybe a tennis ball, right? So inside it, we can put it, and we'll put it in this actual view of storage tank. It will be like this. Yes. And again, we can have, we can also ask the ice storage. Yes, we can also use the ice storage as a phase-change material. So normally, if you use, in case of ice storage, we may require a primary and secondary fluid. If you use the phase change, we can use only a single loop. Even the chilled water supply itself is more than sufficient to cater the need of the thermal load. That is why we always prefer phase change material stored, supported for cold storage applications. And this is the typical pictorial view of a cold storage system. If you look at that, this is the storage container. It's again an experimental setup, lab scale experimental setup created by Mansoor Ahmad et al. And it's published in International Journal for Scientific Engineering and Research, the year 2013. So here, this is the cold storage tank. And the cold storage tank, the inside, this is the outer area, it's insulated area. So inside that they have the PCM, right? They have the phase change materials. The all other, or it's a common that we have a condenser, compressor, expansor device. It's all the same thing. But here the only modification is in the evaporator. So in case of a non-conventional evaporator coil, they installed a phase change material inside the surface. So because of that, we'll check what happens to the COP and other parameter. And again, as far as this particular case, their dimensions of this whole cabin is the length. This is the length, breadth, height, and volume, and this is the capacity they have specified. And this is not my work. This is again work taken from the Mansoor et al. And this is the load versus COP curve that they have been presented here. So here, if you look at this particular thing, this is the COP without PCM panel or without PCMs. Then they have the various PCMs. So if you look at that, this is the highest COP that can be obtained. And this is the temperature versus the time graph inside a cabin. If you look at that, this is the cabin temperature. If you look at that, if you are not having the PCM inside the cabin, the cabin temperature ranges from -20 to almost 5 degrees centigrade. So if you have a phase change material, if you keep this region, right, you can maintain exactly at -12 degrees centigrade, right? So this makes the food product more flexible, and you can maintain the quality, whatever the temperature that you require, that can be maintained, right? This is the phase change material. This is the temperature at which you can maintain inside a cabin. And this is again, there is a storage, PCM storage tank that is for illustrated by Salem et al. It's again a published literature from Applied Energy in the year 2019. So here they have used the secondary chilled water circuit integrated with the PCMs. And this is the PCM tank that have been taken for this particular case study. And this is the flat ice PCM blocks that can be used in this PCM tank to maintain a constant temperature. And this is the temperature profile of that particular PCMs. So here, if you look at that, so this is their phase change temperature. So around almost 26 degrees centigrade. They use this various, this is a ball, right? Inside this ball, they have the phase change material, and these are various ball sizes. And this particular 120 mm ball size will have long, the duration of the latent heat will be very long. This is the pattern for the time, because it can maintain for a very longer duration at 26 degrees centigrade. Okay, and this is the freezing curve, and this is the melting curve. And this is the energy analysis of PCM with and without PCMs. So here, if you look at that, it's again done by Al et al. It's a published work from Applied Energy, and this is the minimum mean minimum temperature, and this is the mean maximum temperature. And here, this black represents the cooling energy stored in the PCM tank, and the cooling energy discharged from the PCM tank to the secondary chiller circuit. So this is stored energy, and this is the released energy. Whenever there's a requirement, they use it. Similarly, this is the monthly cooling energy delivered by the primary chiller to the secondary chiller is presented here. Okay. And again, this the daily average profile of the cooling energy supplied by the PCM and the primary chiller systems. So here, if this is the blue color represents the cooling energy from the PCMs, and this is the primary circuit, right? This is the cooling energy from the primary circuit. And this phase change materials can also be used for a vehicle, for a mobility applications. So what in case of a conventional storage, the same thing we can also have to maintain a constant cabin temperature during the mobility. We can have, in addition to this, the conventional evaporator coil, we have this PCM, right? This and again an evaporator coil. So above that, we have phase change materials. This will ensure a constant temperature inside this cabin. And this is the other cold storage system, which was demonstrated by the other journal or other international journal. So here, this is the cold storage area. This is a cold storage area, and this is again an evaporator coil. So we have a fan. So this is a honeycomb. Right here we have the PCMs. This is a way they can use they place the PCM. And again, I told that we can use the phase change material for storing the heat energy. And again, at the time of discussing, I told that we have the low thermal conductivity, right? So whenever there is a low thermal conductivity, it's again a problem for storing the heat and releasing the heat. So in addition to that, if you use the conventional normal phase change material for storing the heat or cooling energy, and this is the temperature, and this is the heat storage. So this is a sensible area, and this is the latent heat. So normally what happens after storing this heat, it will not take this path. It will again comes down, the temperature will low. So this will takes a lot of energy. We used to call that as a subcooling. So this is the conventional phase change materials. It will follow like this. It will take this path, go straight, and again it comes down and it goes up. This is the conventional PCMs. If you take the water, they have a subcooling. So if you have if you add some impurities, or if you have some added material into that, so we can reduce the subcooling effect. In addition to that, it will freeze and melt at a faster rate. So here there is a typical example. This is a PCM ball. Inside that we have phase change material to enhance this, or to reduce this subcooling, or to enhance this freezing and melting characteristics. They are having a copper rod, or sometimes they used to have some metal. They used to put some metal bar into that. Okay. So in addition to that, what we are suggesting, so instead of putting this bar, we are putting some nanomaterial into that. This nanomaterial reduces the subcooling. In addition to that, to also speed up the storage and discharge period. And these are all the various nanomaterials we used for this particular work. And we have two-dimensional, zero-dimensional clustered, one-dimensional fibers, nano wires, rods, three-dimensional, two-dimensional film or plates, or we also use 3D nanomaterials. And these are all the way at which this nanomaterials can be produced. We have a top-down approach and bottom-up approach. So using this method, we can produce the nanomaterial. And this is the photographic view of carbon nanotubes that is produced. And these are all the amazing characteristics of the carbon nanotubes. And this is again a carbon nanofibers. Maybe at the time of producing carbon nanotubes, there are some difficulty involved in that. And again, it's a costly method to produce carbon nanotubes. So instead of having this, there's a better alternative that is nothing but carbon nanofibers. It's easy to synthesis even in your industry or in your laboratories. And these are all the properties. And this is the same image of the nanofibers that is produced in our laboratory. And this can be used to enhance the thermal properties of pitching material. That material can be used in a cold storage or any other storage applications. And again, this is the SEM image, FE-SEM image of the carbon nanotubes, that is nanofibers that we produce in our laboratory. And again, this is the phase change material. If you look at that, this is a phase change material. If it is a pure form, it look like this, right? It's a highly, the pure PCM will be like this. By adding nanomaterial into that, it changes. It's a transparent. It becomes non-transparent fluid, and by adding this nanomaterial with 0.088%, and this is 1.8%, and this is again a phase change material. And this particular phase change material is a oleic acid phase change material. By adding copper into that, there's a slight change in color. And here, by adding these nanomaterials, we never expect a chemical interaction. It's only a physical interaction. Even by means of physical interaction, there's a slight change in color. So here, this phase change material with graphene nanomaterials. And it's again, this particular, all these phase change materials are patented. So here, as similar to the cold storage, so it can also used in case of a conventional HVAC systems. So here we know that this is a chiller, and this is the occupant or the people, or this is the area at which we are going to have the comfort applications. This is an occupied area. So in addition to that, the chiller unit, we can install this storage tank, and this can maintain a constant temperature. In addition to that, this also used as a passive cooling technology. Maybe if time permits, we will discuss it. So here, in addition to this, the cold storage, it also can be used in case of a heat storage, right? This is a room heating. So this is a solar collector. This solar collector takes the heat from the sun, and it has to store in a PCM ball. During nighttime, the stored heat energy can be used in the wherever we require. And these are all the various phase change materials we produced, and that can be used for thermal jacket applications. And this is the paraffin phase change material with copper oxide, and this is a paraffin with TiO2 nanomaterial. Paraffin with the combinations of carbon, CuO and TiO2. And this is the after synthesizing of the nanomaterials, we used to look the pictorial view, right? The same image, the close view of this nanomaterial, it will look like this. And again, this is again AgTiO2 hybrid nanocomposites phase change material. So here we are supposed to know what's the limit of mixing this nanomaterial in the phase change material, and this can be of a maximum of 0.8%. So after that, there may be a decrease in latent heat, and there's an increase in viscosity that will affect the performance of the phase change materials. And this is what I told, that this is an activated carbon neutrotic phase change material for banana ripening. The activated carbon, the pure PCM look like this. After adding this activated carbon, it will look like that. And the same image of the activated carbon will be looking like this. So here, the interesting thing in case of thermal perspective is, in case of a pure PCM, the thermal conductivity is like that. In case of a solid PCM, the thermal conductivity is 0.2. By adding this activated carbon, if you look at that, the 0.2 unit is increased to 0.4. This is a maximum. Even the liquid thermal conductivity increases, the solid thermal conductivity increases. So because of that, how our battery charge at a faster rate, so we can also charge our PCM at a faster rate. And this is used in case of banana ripening applications. And these are all some of the phase change material. So instead of using this liquid, you can also have the solid powder as a phase change material. Maybe in the forthcoming slides, how this powder phase change material can be used. So this is the pictorial representation of the same image of the micro encapsulated phase change material. In the previous case, the encapsulation may be with the ball size. So here, this encapsulation in terms of the micro interface, it may be of 1 or 2 micron. If you look at that, it may be 1 or 2 micron. So inside this ball, we have the PCM stored. And this is the this is for tomato ripening applications. We have ternary eclectic PCM. I told that ternary eclectic PCMs can be used for low temperature applications. So we have a ternary eclectic etching material with multi-wall carbon nanotubes. So this is the conventional chiller, and we have packed bed, and this is with ternary eclectic PCM with multi-wall carbon nanotubes. And this particular PCM can be used for a tomato ripening applications. This is a storage where we use to store the tomato. Okay, and I told that the micro encapsulated PCMs. So normally, what happens if it's the liquid PCMs? It's like it's a water. We have this a hollow brick. So inside a hollow brick, we used to fill that liquid PCM, and we used to construct the wall. So if there is any damage or if there is any problem, there is a possibility of leaking of this phase change materials. To avoid the leakage issues, what we used to do, we used to make this liquid as a powder, right? And this powder is to be mixed in a cement and plastered over the surface. By plastering over the surface, so it will act as the passive cooling. In case of a building, it will never allow the heat inside the building. Okay, during nighttime, it stores the cooling energy, and during the daytime, it will release whatever the cold energy stored in this particular surface. So this in turn reduce the heat load of any building or any cold storage system. And this particular material is tested in a psychrometric chamber. That facility is available in our laboratory. And this is where we used to test our the brick that is coated with micro encapsulated PCMs. So we have room conditions have to be maintained here, and this is an ambient condition. So in between, we used to place this PCM micro encapsulated pasted over the surface of this brick, and we conducted a performance. And this again, this is for even in case of the cold storage applications, you can also have humidity control. To maintain a humidity control, maybe this can be used for any HVAC or cold storage or in pharmaceutical industries. We have this desiccant coated wheel, and in case of a normal desiccant coated wheel, they use the absorption material. So we used to coat this absorption material with nanomaterial. So because of that, the efficiency of this particular desiccant wheel increases. And this PCM can also used in case of a helmet cooling. Not only can be used cold storage or HVAC system, this also to be used, this is a helmet outer layer. So this the core layer where we can store we can keep our PCM. So this will make to ensure the rider very comfortable. And as I told that this thermal jacket, it's like a normal PCM that can be placed in the jackets, and this can be used in case of a very extreme climatic conditions. So this is where how it would be maintained in case of the PCM bricks. Okay, thank you.
Sir, thank you so much, sir.
Thank you, sir.
So I request all the participants, if you have any queries, kindly post it in the chat box so that I can read out and ask the same queries to sir. Sir, we have some queries.
Yes, sir.
Percentage of energy loss while using PES tank or PCM. Can you please let us know, sir? Percentage of energy loss while using a thermal energy storage tank or a PCM. Is there any losses? That's what the question is. Percentage wise, can you please define that one, sir?
One second. Bonus.
Hello.
Yes, sir. Sorry, sir. There's another call. Sorry. The percentage.
No Sir, we would like to know the percentage of energy loss while using a thermal energy storage tank or a PCM.
Okay. You want to know the loss, right? So normally
sir.
what happens, if you use thermal energy storage system, the loss will be very, very minimum. It's only for at the time of moving from the chiller unit. There is, we have a chiller unit. So we have PCM storage tank. So the wastage is only whenever there is an energy move from the chiller unit to the cold storage tank. If you have a proper insulation into that, obviously we can reduce the whatever the loss. Okay, maybe it's a very minimum to my understanding.
Negligible is what you are saying.
It's very minimum. If you have a proper insulation, obviously we can reduce the loss of energy.
Understood, sir. And sir, do we need expansion tank in a thermal storage system due to the expansion of PCM materials?
That's great, excellent, sir. Normally, what happens? We don't require whatever you said is right. So there is an expansion takes place. So normally we used to place the PCM in a ball, and again this ball will not be completely filled with the phase change material. There is a air gap will be provided. So this will take care of all this expansion activities.
Sir, where will that air go if something is filled up, sir? If I can.
It's a ball. It's a right. It's a ball. It's a completely. You take a typical example of our tennis ball. So inside a ball, if you fill the PCM completely, then whenever there is an expansion, definitely will affect the outer surface, right? So it will maybe or something has happened, or it will damage the ball. So what happens instead of filling 100%, we used to fill only 80 to 85%. So remaining will be the air gap. So air gap accelerate the charging and discharging characteristics. So it will act as a nucleating agent for charging and discharging.
Thank you, sir. Sir, what nanomaterial is used with the water to eliminate subcooling? If it is reduced, how much it is?
Yeah, normally what happens if you use the activated carbon, you can completely eliminate the subcooling effects. Activated carbon is working exactly excellent manner. So normally, even in case we use that activated carbon to reduce the subcooling and to enhance the thermal performance, and that can be used in case of tomato ripening cases.
Understood, sir. Sir, any standards available to measure the performance of a TES system?
Yeah, in standard
or a practice or something.
So normally performance in the sense we are supposed to know the cycling test. The problem is whenever there is a charging and discharging forms of one cycle. So we have to ensure the cycling performance of phase change materials. So for that we have thermal cyclers are available. So using this thermal cyclers, you can go through even 1,000 cycle or 10,000 5,000 cycles. So after that you have to measure the properties of the particular phase change material, whether it's a degrade or there may be a slight degrade in the performance, but it's acceptable.
Okay, sir. Thank you. Sir, do we need to do vacuum for PCM chamber in a cold storage?
Not required, sir.
Not required, sir.
Sir, one query, sir.
Yes.
Are you able to hear me, sir?
Yes, sir.
We can hear you. Mr.
Hello.
Devendra Rao. Yes, we can hear you. Dear participants, request to please post it in the chat box because sometimes there is a signal issue and we are not able to understand what you're saying. Okay, sir. Sir, how to measure charging and discharging performance of a thermal energy storage system?
So normally this charging and discharging is mostly depends upon the latent heat characteristics. So the latent heat.
Oh, okay, understood. Sir.
The latent heat characteristics can be found using the DSC, there is an experimental setup available, that is a differential scanning calorimeter. So using this particular device, you can measure the latent storage capacity of any phase change materials.
Okay, sir. Thank you, sir. Sir, what is the physics behind subcooling phenomenon? If you can help us in a short.
Yeah, that's right. That's right. Normally, what happens once it reaches all this latent heat temperature, the phase change temperature. So normally, what happens? It has to be again because of, it's again it's a nucleation problem, sir. We have to enhance the nucleation effect. If you are not enhancing the nucleation effect, obviously, what happens? That subcooling will take place. So the intention is you have to nucleate it. Normally, in typical cases, what happens if you pour ice water? Sometimes if you place any iron rod, you may find a freezing, right? Do you ever notice that? You can pour a chill water, it will not freeze. If you touch it, it will freeze.
Understood, sir.
Yeah, it's again because of the nucleation.
Yes, sir. Thank you, sir. Thank you, sir. And I think, sir, the standards. Okay, sir. That's all about the questions, sir. I think if there is any other queries, please post it. Yes, energy efficiency and energy efficiency in a thermal resource. How much? I'm not able to understand, Mr. Kamal. Energy
Hello.
efficiency and energy. Yes, please.
Hello, sir. There is a performance is measured in the TS time. Okay, so there will be heat loss through the heat exchangers and also while storing and discharging. So, what is the energy efficiency and exergy efficiency? How it is measured? Hello.
Yes, sir. It's not clear, sir. Your voice is not so clear.
Sir, he is asking energy efficiency and exergy efficiency of a thermal storage system.
Exergy analysis.
Because there will be so to validate it. So the storing and discharging there will be energy loss.
Mr. Kamal, maybe you can mail us. I can share you our mail ID. You can mail in detail so that I can get that same from sir and share with you.
Yeah,
Sir, maybe you can share your mail ID so that people can ask you.
A.S. Kalaiselvam, sir. A.S. Kalaiselvam, right? So my mail ID is yes.
Sir, can you please type it in the chat box and send it to Olympic, sir? Is it possible, sir? So the people can note down and if they have any queries, they can ask you in for a mail.
1 second, sir.
Okay, sir. Thank you.
Okay, thank you, sir.
Kindly mute yourself, sir. Mr. Okay, got it.
1 second, sir.
No problem.
Yes, sir. I think I typed, right?
Yes, sir. We have received your mail ID, sir. Thank you so much, sir.
Thank you, sir.
With this, we can conclude the question and answer session. Over to you, sir. Mr. Krishnamurthy, sir.
Suresh Reddy, treasurer of Chennai East Asia chapter, will present vote of thanks now.
Good evening, everyone. It's been a great honor to be part of this wonderful webinar. On behalf of ISRE Chennai chapter and Repcol 23 host team, I would like to extend my heartfelt gratitude to our esteemed speaker, Mr. Dr. Kalaiselvam. Thank you very much, sir.
Thank you.
And our sincere thanks to Repcol host team who handled this event throughout. A wide round of applause And thanks to all the participants who made this event a memorable one and helping us to make the event a grand success. Thank you, one and all. Thank you very much.
Thank you, sir.
Thank you all.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir. Can I
Thank you,
take
sir.
it, sir?
Thank you. Thank you.
Okay, thank you, sir.
Good morning. Okay. Okay. వర్క్ ఆర్డర్ తీసుకొని చాలు నేను చెప్తాను కదా డ్రాయింగ్ అవసరం లేదు